So today we're going to talk about the word average as it relates to antiderivatives. So we've already talked about average as it related to derivatives. We've done things called average rate. Now we're going to do averages as they relate to antiderivatives and what those mean. And then it leads to a theorem, mean value. The word mean just means average. Those two are synonymous. So we'll talk about that today. So just as a reflection from last week, the area is done as a perfect integral, and there's three ways to do that. So we did geometry, then we moved to using an antiderivative, and if the antiderivative, if you have your calculator, you can do Math 9. So those are the three different ways to evaluate an integral, just depending on what you have. So I would say like these two ways would be your non-calculator ways. So on a quiz, that would kind of be what you would expect on a non-calculator. And then this one you would have your calculator for. So what you'll most likely be asked to do is to interpret what you have. What does your answer mean? Like the last quiz we had billions of gallons of soda, okay, that were consumed during a particular time frame in the United States. So you had the calculator that you figured it out what the Math 9 was, but then you'll be asked to interpret it. So it's a calculator plus interpretation. So the calculator allows you to do much more complex functions, but the stress then is on, do you understand what you're doing? Okay, never would I have ever been asked to do a question like that when I was learning calculus the first time, because I didn't have a calculator that could do all of that. So math has really changed because of technology and what you're expected to learn and do and know. And I think it's going to be like that now in English. Like they're talking a lot in English about AI, right? And AI writing essays, and it's been all in the news lately. And I think, you know what? The math teachers have been dealing with AI forever, because for the last 35 years, we've had calculators that could do all the math for you. And so the emphasis then goes on away from doing the math and having you, like, do you understand what it means, and can you interpret and make a good decision or justify your answer? So math has really changed because of that. Okay, here's what we did first semester. So I want to see the tie-in. We learned that if a function is differentiable, then this is called the mean value theorem. So if you want to label it, this was the MVT, that there is somewhere, at least once, where the prime is equal to f of b minus f of a over b minus a. Visually, we saw it like this. We saw that, you had some function, and if you took the end point and you connected it to the other end point and you found the slope, that at least somewhere else there was another point, and maybe more, but at least once, there was somewhere else that had the same slope. So maybe visually you'd say, oh, it's happening right there, but maybe I see it again happening, right here, and then possibly maybe right here. That's the average value for derivatives. So I want it visually for you to see how that happens. There is the same thing that happens for antiderivatives as well. Okay, so if the verbiage is, if it is twice differentiable, okay, then what can you do with this? So there's a couple things. Last semester, we saw that we could do, and what in my mind I call as going down, but that's just the way my mind thinks of it. I can take both parts of those equations and I can go down a level. So if I take my f prime of c and in my mind I'm going down, okay, that becomes f double prime of c. And on the other side, if I take that f and I go down, I'm doing these to the functions, okay, so then f becomes f prime. The b doesn't change. B's are numbers, so we're not changing those. We're talking about what the function is doing. And then f prime of a, and then b minus a. Again, b minus a don't change. Those are just constant numbers, but in my mind, that's still true. We saw that last semester, okay, that if it says twice differentiable, then you can, and if it said thrice differentiable, you could do it again, or however many times it says it's differentiable. All right, the thing with, now that we're in second semester, the thing that's with antiderivatives is you can go up with this same relationship. If it's true for the average rate, then it has to be true going up as well. So let's see if we can develop what that might look like. If I went from f prime and went up, how would you write that?
The integral?
No, from f prime.
That's just f.
F, okay? So it could be f of c. And then on the other side, if I went quote unquote up, what would happen to the lowercase f? Okay, it becomes capital F of b minus capital F of a over b minus a. That is also true. So the theorem that you learned first semester is true still in second semester at every level, at the first derivative level, at the second derivative level, but also at the antiderivative level. We could take that up again if we wanted to. We could take both sides. What would happen to the what would happen to the lowercase f on the left side? What would happen to that? Become capital. What would happen to the already capital F? It would become that like double capital F or super bold. So you can do this many times. This true statement is true at every level of math. Okay, this is called, we call it the mean value theorem in derivatives. Okay, again, we saw that as the MVT. I wish that they had called it the mean value theorem for antiderivatives. That would have been really helpful if they called it that. But they changed the word and now they call it the average value theorem instead. I don't know why they did it, but on the next page, okay, this is where we see it. It is now called the average value. That's the antiderivative version of it. So here it is. This is what we just did. Okay, that is true, that statement is true. And how we evaluate the capital subtraction, capital F of b minus capital F of a over b minus a, is using an integral symbol. That's how we do it. The most common way you're going to remember this is using like a memory trick, okay? And so the memory trick that I would recommend is that in your mind, you identify that as the integral and you identify that as the interval. We call it the integral over interval. The integral goes on the top. The interval, which is b minus a, goes on the bottom. And so you train your mind when you're asked for average value. You're like, oh, average value, integral over interval. I can do that. Integral over interval. And every time you even write that down, integral over interval, it's like points toward the FRQ. Just for knowing that an average value is evaluated as the integral over the interval. Now let's talk about what it means. I've already reminded you in derivatives what it meant. An average value in derivatives meant that the slopes had to be parallel. So what does average value mean for antiderivatives? So here we go. Okay, that's C value. So remember, for when we were in derivative world, it was the tangent line right there at that C value was parallel to the other tangent line, the secant line that connected the endpoints. That's what it meant in derivatives. In antiderivatives, it means at this point here, if you make a rectangle that's partially under and partially over, as is drawn in here, that the area of that rectangle is the exact same as the area of the integral itself. In other words, this area that's too much and this area that is too little are exactly canceling each other out and giving you the exact answer of the integral. So here's a way I like to think about it. I would say, anybody have fish tanks at their house? Okay, we used to have this beautiful saltwater tank with some tang and this was when my kids were younger, and then my son poured 7-Up into the tank and it killed everything. So no more fish tank. He thought they were, well, there were bubbles in there, so he thought, his drink had bubbles, and so he would just give them something to drink. Yeah. All right, anyway, so
That's so funny.
Imagine you have this fish tank, okay, and you gave it a really good shake, right? Like a wave pool. So what would happen to the top? It would all be like wavy in water, okay? And then when it would settle again, now I would have a nice smooth top. So I imagine that what this mean value theorem to me is like, it's like a function that has a really wavy top to it. And if I was figuring out the area under there, and I imagine it's like water with a bunch of waves. And if that, when that water settles, it would settle into the shape of a rectangle. So there has to be some rectangle where the area is exactly the same, where all the high parts and all the low parts would level out and it would be just completely flat. That level happens at letter C, and it's guaranteed to happen, okay? That value, wherever that's going to settle, is going to happen at letter C. That is what the average value is, and that's what its meaning is. So you can know how to do it. The how to do it is always computing integral over interval. We'll practice that. But the why or the what it means is, to my mind, it's imagining that that's what would happen. If I could smush all that area down to make it flat, this is where it would settle. So let's try it. Let's find the average value of the parabola 2 minus x squared on the interval value from 0 to 4. Okay, so let's do it first, and then we'll connect it to what the visual means. So average value, and in your mind, hopefully you'll start to train yourself, integral over interval. The integral would be set up from 0 to 4 of the equation 2 minus x squared dx over the interval, which would then be 4 minus 0. So now we're going to do the math. We do it by calculating the antiderivative. So the antiderivative of 2 is what? 2x. The antiderivative of x squared is x to the third, then divided by 3, plus the number c from 0 to 4. And I'm still over the interval of 4 minus 0, which is 4. Okay. All right, and now I evaluate this. So that would be 8 minus 64 over 3 plus c, and then minus a whole bunch of zeros, all over the number 4. So I distribute my negative. As I distribute my negative, the c's cancel out, the zeros cancel out. My numerator is left to be 8 minus 64 thirds. In common denominators, that would be 24 thirds minus 64 thirds. Still all over the number 4. So 24 minus 64, that's negative 40 over 3, all still over the number 4. So I can simplify that to be negative 10 thirds. All right, that's the answer. Hey, so what does that mean visually? All right, so visually, let's try and draw I don't like that. Parabola. Parabola is going to start at the number 2, and I'm going to go 0, 1, 2, 3, 4. So the parabola comes down as a parabola, kind of all the way down like that. So I have area both above, but I've got a lot more area below. And what the number negative 10 thirds means is if I find negative 10 thirds on the y-axis, and if I were to draw a rectangle, that rectangle would have the exact same area as the green and the yellow combined. Okay, that rectangle has the exact, the base and the height of that rectangle would be the exact same as the green and the yellow combined. That's the position of the average value. Sometimes a follow-up question they ask might be, at what x value does this occur? So you need to find the intersection point of where 10/3 slices through the parabola and figure out where is that happening, okay, at what position. So mathematically, that would be, where is 10/3 the same crossing through the parabola? So where does 10/3 equal? 2 minus x squared, and then it's just some quick math on that, where you subtract and you figure out where that's happening. So subtract 2 from both sides. That would give you negative 16/3 equal to negative x squared. Since they're both negative, you can divide both by -1. So I can get rid of my negative signs. Come on, get rid of my negative sign. There we go. And then I can apply a square root. And I would have both plus and minus the square root of 16/3, but clearly this is the one that's the square root of positive 16/3, because that's going to be the one that's between 0 and 4 on the x-axis. All right, so what I'm going to just do with you is several sample problems. We're just going to practice the mechanics of how to do it, and then we're going to understand what that means. Okay, here's a non-calculator one. So you would need to be able to do all of this, including making the graph, without your calculator. All right, find the average value of this absolute value function from 0 to 3. All right, so mathematically, we're like, okay, integral over interval. Now, you don't have to write the words down every single time. I'm just doing it now while we're getting the hang of it. But our integral would be the integral going from 0 to 3 of parentheses 3 plus absolute value x minus 2. It's not the absolute value of the whole thing. The absolute value is only on the x minus 2 dx. And then the interval would be 3 minus 0. Now here's where we might be a little bit stumped. Okay, there is no antiderivative for an absolute value. Okay, there's antiderivatives for square roots and sines and logs and all these things, but there's no antiderivative for an absolute value. So what were some of the other methods that we talked about of ways we could do this? Okay, we could do trapezoids. So you're thinking some kind of geometric method. Okay, I can't use my calculator and I can't use my antiderivative. So think back, I'm just gonna bring it, you don't have to go on your notes, but I'll show you, back to here. If I can't use my calculator and there is no antiderivative, there must be another way. There's always another way. And the way, okay, that they're giving, okay, this has gotta be a geometric way for me to do it. All right. So in order to do a geometric way, I need to know what an absolute value looks like. Everybody remember? And what does an absolute value look like? A V. Okay, and what's happened to this particular V? It's up 3, but what else? 2 to the right. Okay, 2 to the right and up 3. All right, so let's get a visual here. If that's where 0 is. Okay, it's 2 to the right and it is up 3. And it's producing a V graph. And my interval is going from 0 to 3. So what shape do I have here? If I'm going to do geometry. How many trapezoids? There are 2. There are 2 trapezoids side by side. Where's the dividing demarcation? Okay, so there is a 2 trapezoids side by side. So I need to figure out the geometry on this. So I'll do the first trapezoid in yellow. Okay, and what is the area of that? Again, remember the trapezoid is 1/2 base times, or 1/2 of the height, left height, and the right height, and then times the base. So what is the left height?
You put it into the 5.
5. Very good. Okay, the left height is 5. What's the right height above 2? 3. Okay, so if the heights are 5 and 3, then what's the total area of the yellow section? How'd you do 8? No.
5 plus 3.
Uh-huh.
1/2 times quantity, 5 plus 3.
Uh-huh. And then multiplied by the base of 2. So this value is 8 for area. Okay, and then let's do a green trapezoid right next to it. Okay, so the green trapezoid, what's its other height on the other side? 4. Okay, and so what's its value? 7/2. So what's the total combined green and yellow value if you add those both up?
23 halves.
Okay, 23/2. That's the integral part. That's the numerator. The denominator is still the interval of 3. And so the total value, 23/2 divided by 3, would be 23/6. So what does that 23/6 mean? 23/6 means that would be the height. If you could settle this trapezoid, the big trapezoid on the left and the other trapezoid on the right, if you could settle them down and make a rectangle that's 23/6 high, that would be about right here as a rectangle. And that rectangular height, that's 23 high, so 23/6 from top to bottom, that rectangular height would be exactly the same as the green and the yellow put together. Okay, that rectangular height, that's the meaning of it. That those two things would come out to be equal. Then they might say, where does that occur? In other words, where does the 23/6 intersect with the absolute value? How many times does it intersect? Yeah, there are two possible answers. It intersects once here, but it intersects once here on the other side. So how do we find that? You know, how do we solve those values? Okay, so what we need to do 3 plus x minus 2 being equal to 23/6. So you got to remember how to solve absolute value problems. Okay, first you got to move the 3 to the other side. That would be 23/6 minus 3, which I can change to a common denominator. Instead of 3, what should I use? 18/6, okay? So that would be x minus 2 equals 5/6. Okay, so I got rid of the 3. What's the next thing to get rid of?
Absolute value sign.
Okay, how do I get rid of absolute value signs?
Into 2.
Okay, it's like when you have square root. It's the thing you got to remember. If I'm going to get rid of the absolute value signs, okay, erase that one and erase that one. Then on the other side, I have to put plus or minus. Because now that I'm taking the absolute values away, it's no longer guaranteed to be positive. It could be positive or negative. Then I add 2. So this will be 2 plus or minus 5/6. And that's how I'll get both my answers. I'd probably change that to be 12/6 plus or minus 5/6. So one of them is 12 plus 5. That'll be 17. The other is 12 minus 5. That would be 7. So those are the two places, either 17/6 or 7/6, yeah.
So the actual answer to the question is 23/6, right? But then the point is like an add-on.
Right, it's like a part B. Yeah, 23/6 is what's called the average value. So that was the question, find the average value, okay? And so these are the follow-up questions they could say. They could say, find the average value. All right, I did, 23/6. They could say then, what would the area be of a rectangle that was formed at that? So now you've got a height of 23/6. And then what's the base? 3. Okay, so figure that out. That could be part. And then the next, where is this occurring? What x values is that occurring at? That could be like a next part. So a follow-up part. Yeah. Okay, let's try it again. All right, this one's an ln. So you'll get to use your calculator this time. Okay, so this would be calc needed. All right, so grab that out. Find the average value. Okay, you have to write, you don't have to write the words integral over interval, but you got to write the integral over the interval itself. So average value is going to be the integral from 1 to 5 of the function 5 plus ln x quantity dx over the denominator 5 minus 1. All right, so we've done one of our problems with antiderivatives. We've done one of them with geometry. This one would be a Math 9. So you should be able to do them any of those ways depending on what you have. And so then why do I need a Math 9 for this one? It's because I can't do an antiderivative ln either. I can't do an antiderivative of absolute value. I can't do an antiderivative of ln. And so I would use my Math 9 to evaluate that. All right, so you can go ahead and do that. So go ahead and then just somebody tell me what you have. And I know the denominator is going to be 4.
Negative 24.047.
And I just would like a little, okay, so that just doesn't seem right to me for some, because it can't be, I'm just thinking like it can't be negative, because if I'm picturing in my mind what a natural log looks like, a natural log is all above the x-axis from 1 to 5, so.
So positive 24.
Okay, so it's positive 24 point.
047.
Okay, now use all the decimals on your calculator. Are they still all there? Mm-hmm. Okay, now divide that by 4. What do you get? 6.01, so 2. All right, now connect it to the visual representation. Okay, so I know that natural logs look like this. Then they cross at 1, 2, 3, 4, 5. And so this area was all above the x-axis. So this has a base of 4, but its top is curved, which is why geometry didn't work, because it was a curved top. What the 6.012 means is that I need to make a rectangle that is 6.012 tall and go straight across. And that rectangle that is 6.012 from top to bottom, that rectangle would have the same area as the yellow. That those two area things are exactly the same. And then the final question, at what x value does this happen? So I would find the intersection. My hunch is it's going to be somewhere in the ballpark of 3 point something, just looking at it, but my drawing might be a little off, might not be to scale. And so I can solve that by taking 6.012 and setting that equal to 5 plus ln x. Now on your calculator, you should have more decimals than 6.012. So use all the decimals you have. Don't just round it when you're solving it, because when you round, if you would round, so for example, if you would have rounded back at 24.047 and divided, you would have not gotten 6.012. You would have gotten 6.011, which is slightly off. And then if you take your 6.011 and you solve it the rest of the way, you're going to be off again. So keep all the digits in your calculators as long as you can.
Because it's ln x plus 5, would that intersection on 1 be moved up 5?
Intersection on 1. Oh, yes, sorry. Yep, thanks. My x-axis should be moved way far down. Should be down here, like that. So there's a lot more. Yeah, I forgot to slide it up.
Wait, so is 6.02 plus 5 or
Nope,
is it?
nope, it's already. Okay, so we'll subtract 5, so that's gonna give me approximately 1.012, but of course you have all the rest of the decimals on your calculator. And then how do we finish solving for x? What do we?
By E?
Yeah, okay, we're gonna take an e on both sides. Okay, so an e on this side and an e on that side. So x is gonna be e to the 1.012, but again, you should have all the values stored on your calculator as you're evaluating that. Okay, what does that turn out to be? Is it almost 3? It's pretty close. Oh, it's close. Okay, 2.751. If I had remembered to move mine up, I think I would have had a better estimation. Okay, and that's the x value where that is happening. Okay, at 2.751. The base is still from 1 to 4, but 2.751 is where it's happening, where the height is exactly that high.